in the room. So we are already broadcasting, Karina?
I think it's
The YouTube is running?
yeah.
Okay. Okay,
Yeah,
we can
it's
start,
running.
Professor. We can start, Professor Hook. Good afternoon from Chile. Hello, everyone in the room. So we are already broadcasting, Karina? I am hearing the transmission with return, Karina. Maybe there is a mistake there.
Yeah.
No?
And now you have returned?
I think we are good now.
Yes.
Okay.
Sorry.
Hello, good afternoon. My name is Felipe Ochoa. I am a faculty of civil engineering at University of Chile with emphasis in geotechnical engineering. And today we have the first seminar of our academic seminar of the spring, this 2022. And the guest we have today is a living legend of geotechnical engineering. We have the pleasure today to host Professor Evert Hoek. Professor Hoek, hello, how are you? Very nice to see you. How is everything in Vancouver?
Very good. Thank you, Felipe. Thank you for the introduction.
How is the weather over there in Vancouver? Good weather
Very
these
good.
days?
Beautiful.
Very good. Very good. So we are very happy to have you here, to have the possibility to have you here in particular, sharing your experience and your knowledge with us on the topic of rock mechanics, where you are a must reference in this topic, of course. And just before starting with your lecture, which will be mainly a video for a deeper discussion later, I wonder if we can make some quick questions to you regarding your background and stuff like that. So how Mr. Evert Hoek became Professor Hoek? Where did you study? How was your background? The different countries where you have lived in?
Okay, so I was born in Zimbabwe in Africa 89 years ago.
How many years did you say? 90?
89.
89.
89 years ago. And I was educated in Zimbabwe, and I then obtained work in the Council for Scientific and Industrial Research in South Africa, where I became involved for the first time with rock as an engineering material. And I worked for 9 years on the problem of rock bursts in very deep level mines. In those days, the mines in South Africa were approaching 3,000 meters of depth.
Wow.
And so I worked on brittle failure of rock. And then later, in 1976, I moved to London, England, where I joined the Imperial College of Science and Technology, specifically the Royal School of Mines. And I worked there for 8 years as initially as a reader and then as a professor of rock engineering at the Royal School of Mines. And that's where the professorship comes from. I then left university and joined Golder Associates, a large Canadian consulting company in geotechnical engineering, and I moved to Vancouver. I have lived in Vancouver ever since, except for a period of 4 years when I went to the University of Toronto as a research professor of rock engineering. And I returned after I spent 4 years there. I returned to Vancouver and have worked ever since as a consulting engineer until I retired about a year ago.
I see. I see. A long career.
Long career.
Long career. And among all these all these topics related to geotechnical engineering and rock mechanics, I guess you have had many challenging projects and many challenging research projects also. Do you have a favorite project or a project that you remember because it was particularly challenging, for instance?
Well, I've worked, I think, in many more than 20 countries around the world on a huge range of projects, from mining, open pit mining, underground mining, slope stability problems, dam engineering, underground caverns, tunnels, all over the world. And I have many favorite projects. The one I'm going to talk today is one of the most, one of the ones that I regard as one of my favorites, and that is the Chuquicamata open pit mine in northern Chile. So I'll be talking about that in the video. You'll see that. So it's been a very long career with many involvements in projects and in research projects, both at the Imperial College of Science and Technology, the Royal School of Mines, and at the University of Toronto, where I spent some time as a research professor.
How many times have you been to Chile, Professor?
Oh, many, many times.
Many times.
I worked in Chuquicamata for almost 20 years.
Oh, I see.
Starting in 1991, where I was first appointed a consultant there. And my last visit was in, I think it was 2018.
I see.
It's a long period.
So on regular basis, you would be coming to Chuquicamata in particular?
Yeah, I mean, not every year, not every month, but
of course.
Many times.
I see. So you for sure you have many friends, many Chilean friends.
That's right. Yes, and I had many Chilean students as well. So
very nice.
A close association with Chile.
Very nice. Very nice to hear that. We have seen many of your examples about Chile in your books.
Yes.
So that's why I was asking the question. I just wanted to know a little bit more about it.
Sure.
So thank you very much for sharing those details. Maybe we can talk a little bit more after the discussion that we will be having.
I would be happy to do that. And so the video is quite short. It's only 15 minutes, but it talks principally about Chuquicamata as the example I give you there. And we can then discuss anything you like after that. All right.
So what I will do now is that in Spanish and of course in English, I will give an introductory explanation about how we are going to have the session, just for everyone to be on the same page.
Okay.
So I'll do it first in Spanish.
Sure.
El profesor Hoek nos preparó un video hace algunos días para que este video lo pudieran ver no solamente ahora, sino que también con algo de antelación para poder establecer a partir de esta presentación corta de aproximadamente 15 minutos, tener una sesión de discusión sobre los tópicos que van a ser presentados en esta transmisión que Karina amablemente nos va a ayudar mostrando. So now I turn to English. So the way we are gonna perform this session is that we are gonna have a video showing the main topics that afterwards Professor Hoek will be discussing in detail based on the questions that the audience and of course us will be doing to Professor Hoek. So Professor Hoek, we are ready. We only need Karina to help us with the broadcast of the video, and we'll turn off our cameras and microphones so the focus can be on the video. Thank you very much again for being with us, Professor Hoek. Thank you.
Thank you.
Profesor, usted me comenta si se ve y se escucha el video, por favor.
In response to an invitation from Dr. Felipe Ochoa of the Department of Civil Engineering in the University of Chile. I'm presenting this discussion on using rock and rock masses as engineering materials. A brief summary of the basic principles of rock and rock mass strength, followed by a discussion of the application of these principles to a practical example, will be presented. You'll see that there is a lot of text on the slides in this presentation, and this is unusual for me. I normally rely on good illustrations and minimal text for my presentations. However, since you do not have access to some of the basic material that I've used in preparing this presentation, I've decided to include a discussion of this material in some of the slides, and so you'll be able to read this when you have obtained a copy of the video. This illustrates a triaxial cell showing a core specimen with a yellow rubber sleeve to protect it from direct contact with oil, used to apply confining pressures. This cell permits us to obtain a full triaxial stress plot with strain gauge instrumentation for the calculation of deformation modulus if required. The illustration on the left shows two halves of a specimen which was loaded triaxially to about 90% of its uniaxial compressive strength before cutting it in half and polishing the surfaces. Shear failure cracks are visible in the polished faces of the specimen. The Hoek-Brown failure criterion is used to characterize the failure process, and some of you will be familiar with this, with the equation presented here from a reference listed at the bottom of the slide. I'd like to add a note that all my publications and videos are listed and can be downloaded from the Rock Science website given at the bottom of the slide. In my experience, and based on my original training as a mechanical engineer, I prefer to use a lathe for all specimen preparation work in triaxial testing. This includes cutting and grinding of the ends of the specimen, as shown on the left, and cutting profiles of the specimen, as shown on the right. The published triaxial test results for marble are shown in this plot, with the Hoek-Brown failure criterion fitted to the central portion up to a transition from brittle to ductile failure. The tensile tests, based on the use of dog bone-shaped specimens on the left, are shown with a red line fit to the generalized Fairhurst-Griffith plot. This tensile cutoff is applicable to all intact rock specimens without inherent weakness planes. For rock masses, I generally consider that the tensile strength is 0. This table gives a summary of published values of the deformation modulus E, the uniaxial compressive strength sigma Ci, and the Hoek-Brown constant Mi for a wide range of rocks. This table was prepared by Dr. Trevor Carter, a former colleague of mine when we both worked for Golder Associates, and we found it to be very useful during the early stages of projects where very little test data is available. I've highlighted the row referring to marble, and you'll see that the average values are E equals 77 GPa, sigma Ci equals 90 MPa, and Mi equals 9. From the results on the previous slide of this plot, you'll have been prepared for a range of different intact rocks and different Mi values. Note that the Hoek-Brown curve has been projected backwards into the tensile region to the intersection with a tensile cutoff. This does not provide as good a fit as the generalized Fairhurst-Griffith plot shown on an earlier slide, but it is very close, and it's a good approximation, which is adequate for most design work in rock engineering. The Hoek-Brown criteria for intact rock can be extended to rock masses by generalizing it as shown on this slide. The constants MB, S, and A can be varied to accommodate discontinuities such as joints and blast damage. The Geometrical Strength Index, GSI, was introduced by Hoek and Marinos in 2000 to provide a basis for incorporating jointing and disturbance into the Hoek-Brown criterion. Note that this interpretation of GSI can only be applied to a heavily jointed rock mass, which can be treated as an equivalent to a homogeneous soil. An example of the use of GSI in a very large open pit mine will be given later in this lecture. This slide shows examples of GSI in different rock masses, and it's very largely self-explanatory. This slide illustrates the Chuquicamata open pit copper mine in 2013 at the beginning of a transition from open pit to underground block caving, which was implemented in 2019. I was invited to act as a consultant to the Chuquicamata mine in 1991, and together with Dr. John Reed, an Australian engineering geologist, we laid out a program for testing and data collection for the geotechnical group of the mine. This program was implemented over many years and resulted in a large and reliable database summarized on this slide. The geotechnical database assembled between 1994 and 2012 by the geotechnical team on the Chuquicamata mine is presented here. Note that the footnote in red summarizing the quantity of bench mapping and core drilling is very impressive. The data collection process was very expensive, but it is consistent with the magnitude of the design process for slopes and underground works of one of the world's largest mines. The following slides illustrate the design process for the crusher transfer station in the east wall of the Chuquicamata open pit. About 130,000 tons per day of ore was loaded from the M1 crusher on the pit floor onto the twin conveyor belts in the M1 tunnel. This ore was transferred onto twin belts in the K1 tunnel in the transfer station shown by the large red arrow on the top of the slide. This ore was then delivered into the E4 crusher and then onto the stockpile for processing. In the 1990s, Chuquicamata produced up to 650,000 metric tons of refined copper and 13,500 metric tons of molybdenum annually. In 2018, it was transformed into an underground block caving operation with an anticipated annual production of 366,000 tons of copper and 18,000 tons of molybdenum. The underground crusher station was crucial to the Chuquicamata open pit mining operation, and details are presented in this slide. The cavern itself is a very simple underground cavern with two tunnels for entry and exit of the conveyors. Minor stabilities with one end of the cavern were experienced, and a detailed analysis was carried out to provide any additional support to ensure that such problems did not occur again during the remaining years of operation. The approximate location of the transfer station access tunnel in the east wall of the open pit is illustrated in this slide. This table presents details of the rock types used in the analysis of the transfer station in the east wall. Plots of the Fortuna granodiorite and brecciated sandstones included in the analysis of the transfer chamber are shown here. The mining-induced deformations of the east wall of the open pit and transfer chamber were analyzed using a three-dimensional discrete element model carried out by Pedro Verona, representing Itasca, and Felipe Duran, a member of the Chuquicamata Geotechnical Department. I was responsible for monitoring this analysis and assuring that the critical issues were addressed. The Fortuna granodiorite rock mass in this 200-meter high section of the east wall was incorporated as a homogeneous rock mass. The very important structures shown in blue were included as planes in this model. Details of the three-dimensional discrete element model are shown in these slides. A comparison between the computed and measured horizontal displacements in the rock mass surrounding the conveyor transfer station is illustrated here and shows that the analysis was representative and realistic of the actual conditions encountered in the field. Displacement measurements in the Chuquicamata open pit were carried out using 1,000 prisms and a number of remotely controlled theodolites, as shown here. Measured displacements were telemetered to a central monitoring station for interpretation. Radar units were used for measurement on specific rock elements of interest, but without installed prisms. These units can measure millimeter movements at a distance of up to 3 kilometers. Results of the numerical analysis of the transfer station showing displacements in the surrounding rock mass are presented on the left. This analysis permitted the designers to determine what additional support using tension-grouted cables was necessary in order to ensure that no instability problems could occur during the remaining life of the transfer station. The waste ore from the open pit mine, which at the time of this photograph was about 900 meters deep, was transported to surface in 400-ton trucks, as shown in this slide. This slide shows 400-ton trucks hauling a total of up to 370,000 tons of waste rock per day from the base of the open pit. This 11-kilometer drive required about 2 hours, and as you can imagine, the cost of this process is very high. In fact, the very high cost of transportation of open pit mine waste and ore from the bottom to the surface is a very important factor in the decision to convert the mine from an underground to a block caving operation. The block caving operation in Chuquicamata is still very young, and I do not have any details to present to you. However, this is a good illustration of the Palo mine in South Africa from an analysis carried out by Dr. Brianne Sainsbury in Australia. And it illustrates the development of the block cave from an underground extraction level and gradual convergence with the open pit behavior and the creation, in the case of Bora, of a large slide in the open pit. What is important in looking at this analysis is to avoid contamination of the ore with waste from the open pit mine, and this requires very careful planning of the sequencing of different levels of open pit, of underground block cave mining. This is a look into the future and demonstrates the development of extremely powerful analyses which will be used in the future for block caving studies and the design of the interaction between these and overlying open pit mines. Thank you for your attention.
Thank you very much for that video with very fruitful information, Professor Hoek. Now we open the floor for discussion, or you would like to introduce the elements on risk assessment, Professor Hoek?
Let's start with a discussion and I'll see if I can bring up the information for risk assessment as we progress. But if there are any immediate questions related to the, I've lost my information there. Let's start with a general discussion. Any questions that people have on the basis of the presentation, which in watching it, I found was rather a little bit too fast. There was not enough time to absorb the details. So
are there any details maybe that you would like to add to some of the points of the presentation?
Well, I'll talk about risk in a moment, but first of all, are there any questions that people would like to ask?
Any questions for Professor Hoek? Let's see, because we have two sources of questions. Some questions from here, from the Zoom room, and some others from YouTube. Let's see. See, I think people will be formulating some questions. I would like to do some questions. In the meantime,
Sure.
Other questions come. Is specifically on the topic of rock slides, particularly thinking of mega landslides.
Yes.
We have had some huge landslides in the south of Chile, in the area of Patagonia, in areas where in the past it was this was totally covered by snow and glaciers, but due to the period we are living, there is a lot of unloading due to the disappearance of these huge loads on the hills of these mountains. And we have had these landslides with sizes that can go up to 15 million cubic meters.
Yes.
One of the hypotheses that had been stated to address these failures are related to progressive failure. Considering that considering that aspect in which not necessarily we are dealing with brittle material, but a material experiencing creep, how the Hoek and Brown criterion, for instance, could be applied somehow to address this from a numerical perspective. Because maybe you can, some of the hypotheses that we have worked on is that you can think and use the Hoek and Brown criterion, thinking of exclusively with the residual strength. Would that be a plausible way to solve this kind of situation?
Is a very difficult issue because we know very little about how rock masses behave in terms of time-dependent failure. You're obviously looking at a very complex process where, as you say, in a large landslide or a large, even an underground failure in a mine, the rock doesn't necessarily fail instantaneously. There are situations where the stresses are so high and you're dealing with an intact rock that the rock does in fact burst. Implosive failures like that we call rock bursts, and those are the type of failures that I mentioned when I was working first in South Africa, where the mines were very deep, the rock was very intact and very hard, and when it failed explosively. That's very unusual. In most cases, and particularly the cases of slope stability that you're talking about, the failure is progressive. So that what happens is that many things change. You have an assembly of rock that was broken up during formation when the rock was placed in whatever form, as a intrusion or as deformation in a material that had been deposited volcanically or whatever. There are changes that have occurred that have caused the rock mass to break up into smaller pieces. So you're not looking at huge pieces. If you think of the slides I've just shown for Chuquicamata East Wall, which is at the time that I take those photographs, about 900 meters high. The rocks that you saw from a distance from the other side of the pit looked like grains of sand, but they were in fact 3 meters, maybe 5 meters blocks of rock. And in all of the discontinuities were broken pieces caused by sliding and rotation of the blocks. So it's not a simple solution of just taking a triaxial test, measuring the residual strength.
Exactly.
That's way too simple. You have to look at much more than that. And as I say, our information is not good, but you can hypothesize that the failure would be progressive. So if you look at the whole slope, what are the groundwater conditions? What is the unloading due to melting of the ice? Each of those has an impact, and you could visualize a sequential analysis where you apply each one of those one by one and see what happens next, and then the next change when the snow melts, and the next change when you have heavy rainfall, and so on. Now, this is not a simple process. This can take a very long time, and each component of the analysis is not very accurate because we don't know. For example, if you have a heavy rainfall area in a slide like that, what does it do to the groundwater? In some cases, we have slopes that have been instrumented, we have piezometers, we measure the groundwater change. And I can think of one very, very large slide in Canada, north of Vancouver, where we have basically soil type slopes, but huge slopes, I mean, many, many kilometers in size, and where there are piezometers that show the changes in groundwater conditions throughout the year and with storms and so on. But in the case of a landslide, you don't have that instrumentation. In fact, at the very best, you might have some survey results from work that people have carried out. That's the best information you have. So it ends up being, in many ways, a hypothetical study. You have to look at each stage and say, okay, what if the rock mass is like this and all the snow melts, or there's a small failure at the bottom? What does that do to the geometry of the slope? And what happens if you have extremely heavy rains and the groundwater conditions change? And it becomes a question of hypothetical analyses. And that's the state of the art. We have no means really of measuring the properties of many millions of cubic meters of rock in a landslide which might be 2 kilometers high, where you have an ice load, where you have all of these things going on. That's the extreme case. But even in simpler cases where we're just looking at a simple landslide, it's very difficult to get all the information we need. And most of the studies that I've done in my career have been hypothetical because there hasn't been enough information. Even on Chuquicamata, which is probably the best instrumented open pit mine I know of in the world. There were 1,000 prisms fixed in the rock mass in the pit, and these were monitored about every 20 minutes by 7 theodolites automatically scanning. So we have a huge, huge amount of information. But even then, there were some surprises that we had that surprised us. However, if you look at the back of the slides that I showed you, you have a 1,000 meter, almost 1,000 meter deep pit with very steep slopes. At the bottom on the east wall, the slope angle was 53 degrees. There have been no failures in that slope. So you have to say that for 20 odd years, all the information that was gathered, all the analyses that were done by many, many people on the staff at the mine and by consultants who came in, gave us sufficient understanding to mine that pit. As I say, a very steep, very daring design, but it worked. And the first time it failed was when it was undercut by block caving underneath it. In fact, I don't know if that's even happened yet. I haven't been there since block caving really started. But in the case of Bora, it was the caving induced by underground mining that caused failures in the slopes. There had been no previous failures.
That in that case, the failure, maybe I'm confused, but if I remember well, in that mine, what happened was that initially there was a huge excavation, and then they did block caving, right?
Yes.
I see.
And so it was the disturbance of the block cave underneath that caused movements in the rock mass around the mine and slope failures. Now, at that stage, the slope failures were not important. They were not affecting the mining because the mining had been stopped. And eventually the same will apply to Chuquicamata. I don't know what is the balance today between the underground block caving and the open pit mining. I think they are still mining parts of the pit by open pit because the block cave is still very young. But as the block cave grows in size, it will begin to have an impact on the pit. And eventually the open pit mining will stop and it will become completely underground. Now, I haven't answered your question very well. And the answer is we don't know the answers.
Well, yeah, of course. It's a challenging topic. It's a very challenging topic, and we only try to apply the tools we have to solve a problem in which it's very difficult for us to handle all the information that we actually need to solve it in a better way.
Yeah, but if you look at the example that I've shown you of Chuquicamata, since 1991, there were thousands of pieces of information gathered, monitored movements by radar or by theodolite, tests on rock, measurements of movements underground. All of those things were there. And so with all of that information, we've been able to use the technology to design a mine which was stable, very stable. You saw the pictures at 1 kilometer deep. And now we're going underground. You can't talk about the same thing for a landslide. You don't have 1/10 of that information. So you can only guess. Yeah. You can only guess at the sequence of things that are happening. It's still worth doing that because it gives you a feel for how sensitive is the slope to this kind of loading or this kind of failure or this kind of degradation of the rock mass. But we don't have anything like the information that we had for Chucky, which is
exactly.
The best I think of.
Yeah, that's why I was wondering if it's a plausible hypothesis in the sense that, for instance, when we have done this in the past, to appreciate the effect of loading and unloading, yes. Right? If we apply the Hook and Brown criterion, we can observe through numerical modeling that you can see the evolution of a fracture. So somehow it's like the Hook and Brown criterion is working it's like taking a picture for each step load that we do. And you can see how there is a development of a surface failure that it might explain somehow the issue. And we complement it, of course, with numerical, with experimental work, and also with some LiDAR and INSAR measurements, particularly in a work that we perform with Professor Sergio Sepúlveda, a professor who is in Simon Fraser University.
Yes.
these days, a former professor of our university here.
Yes.
And what do you think about those tools, Professor? The new tools that are being applied in the mining industry, like LiDAR, INSAR, particularly INSAR, which is seems to be very promising.
Well, I think as these developments progress with the use of these new tools, optical measurements and many kinds of measurements that we can now do, obviously we will increase our knowledge, but it has to be linked to analyses which are in many ways still hypothetical, because we have no accurate means. As a mechanical engineer, if I was asked to design, let's say, the spar in an aircraft wing, I knew precisely what the material was. I could define the curvature of every component. I could calculate with a very high degree of precision. And that is what aircraft designers do. We don't have that information at all, not even close. So it's greatly beneficial to do these kind of analyses, because we're teaching ourselves what happens if, using this model, you see a potential failure developing. What does that actually mean? What it does mean is that our analyses carry a very high or a very low level of accuracy. The probability distribution wide in their size. So we have to recognize that all we're getting is a good indication of what could happen, but we don't know whether it will fail tomorrow or 5 years from now. We don't know whether the groundwater has to be this high or this high. We know that we can understand what mechanics are taking place, but we can't calculate them very precisely, because there's no way we can get information of the quality you need to do that, except in exceptional cases. And in terms of open pit mining, Chuquicamata is the best case I can think of. So you're lucky to have it there. And if you have the opportunity of taking your students up there at any time, it's very, very rewarding to see how everything is done. I haven't been there for several years now, and so much of the emphasis has moved underground, because it's the underground mining that is now gaining emphasis. So it's a little bit of a mix-up at the moment, but nevertheless, it's still well worth visiting.
In Chuquicamata, you mainly deal with brittle rock, right? That's the main.
No, I wouldn't say that. The fault zones were very, very poor quality. The shear zones that occurred in there were very poor quality. So when you
there are a lot of how you call it,
faults. The faults, the very important structures we call them, which could be faults or joints or shear zones. Some of that material was very, very poor. So you could have if you think back to the slide, you could have a 1,000-meter high slope where the blocks are maybe 5 meters size, but which look like a soil. So you can apply uniform Hook-Brown criterion to that, but then you superimpose on that the faults, the joints, the shear zones, and they have very poor qualities, and they generally define where the failures are going to occur. Sometimes as just one wedge or a plane failure, but very often they interact with one another and locally weaken much, much, much further than we were when I started in this business 60 years ago. We've come a huge distance, but we still have a long, long way to go. And it may be that it's not ever possible to collect all the information we need, because you're dealing with every landslide you look at is different. Different size, different kind of rocks, different mechanics. And all we can do is hope to use our knowledge to the best advantage that we can, and say, you have to be careful with this slope because it can fail. We can't tell you when, but it has the potential for failure. And I remember an analysis done by Stefan Robertson Kirsten on the development of a mine in Chile. And what they did was they made three-dimensional models of every stage of the pit from the shallow mining as it went down, and they came across, including the road designs, everything, very detailed design. And there were places where a failure was going to happen. And so they said, okay, what happens if it fails there? Where do we have to put the highways? How do we have to deal with that failure? And it was a very, very impressive examination, I remember. And a lot of the risk analysis tools that I talked about come from that kind of analysis.
What are the main aspects, by the way, on what you mentioned about risk analysis? In this kind of assessment, what are the main variables that these days you recommend to address? For instance, because the stakes are different when you are in a mine or in a cliff on the coast, for instance, but there is still risk for the society from different perspectives, but the risk is still there. So the balance between the stakes or the stakeholders, if you will.
Let me just see if I can bring up. I've got a PowerPoint here with 4 slides. I'm not sure if we can incorporate it. It's on my screen, but I don't know how to incorporate it into your.
Karina, I wonder if let me check. Maybe let me double check that you have control over the.
Yeah, he can share the screen.
Okay, you can show a screen, Professor Hook.
Okay.
Maybe Karina or I can share it too, if you will.
So if you can see my screen, the whole screen.
I cannot see your screen yet.
Okay, I'll try and give you a bigger view. So I have a screen now which has you filling 2/3 of the screen, and the other third is some slides on risk analysis.
I can show the risk analysis PPT, if you will.
Yeah, that's what.
So and you let me know when to pass it.
I've just got 4 slides, so can you see the first one?
No, I cannot see the first one, but if you want, I can show the slides on your behalf.
Okay, can you do that?
And you describe them.
I'll describe them. Can you do that?
Yeah, of course. There you go, Professor.
Okay, so here we have the issues of risk analysis. So this is a complicated slide, and I have to take a lot of time to describe it. And this comes from a paper by Stefan Taburka, Veselu and Venter, which is referenced there. It's a very good paper, which I recommend that anybody interested should read it. But let me explain that what we see here is on the horizontal axis, the number of fatalities expected in a failure, from 1/100th of a fatality per year, 1/10th of a fatality, 1 fatality per year on 10, 100 across. This is a logarithmic scale. Both scales are logarithmic. So that's the number of fatalities. On the vertical scale, the average probability of failure going from 1 per year at the top down to 1 in 10 million years at the bottom. Okay. And this is a program, this is a plot that's been developed over the years by people working in risk analysis. So let me go here to the point with a big red arrow. Can you hear me and see all of this?
Yes, yes.
Okay, so what the big arrow is pointing to is 1 fatality every 10,000 years. Can I just go back 1 slide? Okay, stay there. And that is the average probability that we as individuals are exposed to simply by being alive. You can fall down the stairs or you can electrocute yourself changing the plugs, but that is one fatality in 10,000 years. That's the basic standard from which we look. Now let's look at, on the vertical axis, I've put a number of points here going from 1 to 11, and these are listed on the right-hand side. So you see the most dangerous is space shuttle flying, which you would expect. And that's about one fatality every maybe 20 years. The next are these two, which are very interesting, 2 and 7. And that's shown on the next slide. Can you move it up one next? There we go. So here I'm pointing to 2 and 7, and those are cigarette smoking of 1 pack a day or cancer. That's the highest, apart from space shuttles, which none of us, or very few of us, will get involved in. That's the highest level that we can either induce by smoking cigarettes or by getting cancer, which is something you can't avoid. And that gives you a fatality rate of about 1 in 300 chance of that happening. The safest is the next slide. Next slide. And this is point 10, which is air travel. The safest actually is being struck by lightning. That has a chance of 1 in, let's say, 5 million. Aircraft travel, flying in an aeroplane, a commercial aeroplane, has a chance of 1 in 100,000. Now, first of all, let me stop for a moment and say, is this meaningful to anybody? Can you understand what I'm talking about? Or do you want me to explain anything else? What do you think, Felipe?
An explanation always helps. Always helps.
What about any questions from the audience? Has anybody?
Let me see. I think now we are receiving questions. I think now we are receiving more questions, but I'm not sure if they are related to this particular topic that we are discussing now on risk.
I have one more slide on risk. Let me move.
All right, and then we can do then we can read more questions. Okay, there you go, Professor.
So this is open pit mining. Now, first of all, there's a very high probability of failure of about 1 in 10. 1 slide per 10 years. Now you say that's much higher than anybody else. But we're destroying the rock mass to release the ore. So we are inducing a failure process. Therefore, the probability of failure is extremely high. The important thing is, how dangerous is it for people working in the mine? And the good thing is, where you have good control, such as in Chuquicamata, you typically have a risk of failure, a risk of fatality of 1 in 100 years or 1 in 10 years. Let's say 1 in 7 years is the frequency of fatality in open pit mining. And in my experience in Chuquicamata, I worked there for a very long time. I can only remember one case where I was called to look at a fatality where a miner had undercut a slope and it had fallen on top of it. One case in maybe 20 years of experience of working there. So, but if you look at some of these others, obviously there are very high probabilities of fatality in mobile drill rigs and some of these activities that are listed. So in spite of the very high number of failures, the risk of fatalities in open pit mining, provided they are well controlled, is very high, is very low. In the case of Chuquicamata, the one failure that I demonstrated there was a very large failure. There were no fatalities of any kind. There was no loss of equipment, because the monitoring that they'd done on movements and so on very accurately predicted when the slide was going to occur, and everybody was moved out of the mine on that day, or maybe a week before. So this summarizes what I wanted to say about risk analysis, and it clearly has a role, because if you plot up the results of your measurements over several years, and you find that you're out of these zones provided by this analysis, which has been done by many, many people over many years, then you have to ask yourself, are we doing enough for safety? What else do we need to do? Okay, questions then. More questions.
You left me thinking about it. I would like to maybe by at the end I would like to do some questions about this, but let's read some of the questions from the colleagues here on YouTube, and let me check. We have some questions. I just need to find it because there are a lot of people saying hello and
Sure.
Thank you for your time sharing your knowledge here. Sure. With us, Professor. So, okay. 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 There are some interesting questions. The first questions. There is one from Nicolás Antonio Castro. And he says. But it's not related to particularly the presentation, but we are going to move forward to those.
Of course.
What led you to be interested in rock mechanics?
What persuaded me to become interested?
Yeah, how it come that you became interested in rock mechanics? It was because of your work in South Africa?
Yeah, because for my master's degree in mechanical engineering, I studied stress analysis and strength of materials. Now, the materials were steel or alloys or whatever, and the strength was how did an aircraft wing behave. Actually, the topic I studied in detail was the stresses in a bolted connection. In other words, a nut and a bolt. What are the stresses in the thread, and where does the bolt fail? And I did it using a technique called three-dimensional photoelasticity, because that was in 1956. The first computers that you could buy as an individual, I bought one in Seattle. I remember driving down to Microsoft and buying a computer in 1983. So there's a big period there where we had no computers, we had no programs, and we had to do it a different way. And so when I was approached by the Royal School of Mines to apply for a position there, they were aware of my work on brittle failure and the progression of failure, and they said, would you like to come and work with us in mining? And I don't know who suggested that we should work in this field, but I very quickly moved into working with rock as the engineering material, not steel or concrete or anything else, but rock and rock masses. And that's really where my history in the field began.
I see. And who was your mentor at the time? Did you have a mentor, or it was a collection of experiences that you gathered to?
Well, the first mentor I had when I worked in South Africa was a guy called Gunther Denkhaus. Dr. Gunther Denkhaus was the director of the institute in which I worked, and he had a lot of experience in stress analysis and strength of materials. And so it was, I mean, he didn't hold my hand every day, but we talked occasionally, and it was very useful having somebody like that. When I moved to Imperial College, it was very interesting because the Royal School of Mines was one of 3 colleges of Imperial College. The other one was engineering geology, where you had some very powerful, famous engineering geologists. 2 that come to mind were Ramsey and Price. And civil engineering had soil mechanics.
Exactly.
Names like Bishop and Skempton.
Bishop, Skempton.
So I worked for many years with all of those people. And that was a very inspiring place to work and helped me.
I'm sure it was. Yes. Yes, I'm sure it was. Very nice. Very, very nice.
And then I moved to Golders, which was starting as a consulting company. And in rock mechanics, I was one of the first people in Vancouver, where the rock mechanics group was set up to work in rock rather than soil, because Golder Associates started as a soil mechanics consultant. And the rock was added to it as a second thought, if you like. And I was involved very much in that establishment of rock mechanics in Golders.
Very interesting. Very interesting. Thank you for sharing that, Professor. So we have another questions. Benjamin Gerhardt. Professor Hoek, what do you consider to be the rock mechanics challenges associated with seismicity and rock bursts in mining these days?
That's a very good question. And I have to say, I haven't worked in that field for many years, but the problems haven't gone away. We are still, in fact, in working in some of the other mines in Chile, El Teniente was one where there were severe rock bursts in the underground part of the mine. And I worked with a group down there on rock bursts for some time. And we made very little progress in that field because it's extremely difficult to control. You are talking about a situation where you are mining, let's say you're doing room and pillar mining. You are creating pillars which you decrease in size. And there are today some very good rules as to how much stress the rock will take in a certain layout. And we have very good 3-dimensional programs that allow us to look at the stresses induced in the pillars, the behavior of the rock. But occasionally somebody will rob a pillar or do something, or we haven't understood it adequately. And we have almost no control of rock bursts if the stresses that are critical to the rock failing are exceeded. The rock will burst, and it can be very violent indeed. There have been many huge rock burst accidents all over the world. I've come across them in Australia.
And many of them lethal.
Sorry?
Many of them are lethal.
Yeah, lethal. Yeah, because if the situation arises where the rock virtually explodes and you happen to be there, sorry, but that's the way it is. And so it's still a very dangerous process, and it's still one over which we have a lot better understanding than we've had, but not yet enough. And there are still teams working on rock bursting as a critical problem. And the difficulty is, I don't think it's to do with numerical analysis. I think we have adequate numerical tools now to look at any 3-dimensional geometry and stress induction. The unknowns come from whether we really have categorized the rock mass correctly, whether there are faults in the vicinity that can slip by. Remember a rock burst in South Africa, which had nothing to do with the intact rock. It was the slip of a fault that caused huge damage. So how do we collect that kind of information? Because some of these projects, Chuquicamata, for example, you're talking about mining 500,000 tons of rock per day. It's very difficult with the technology we have to gather enough information that you have covered every little aspect of the mine where damage could occur. So at the moment, one has to say they are more accidental than they were in the early days. they could happen anywhere, and we had no idea what was happening. Now we understand the problem well, but we're still not in a good position. It's rather like a comparison with driving on the road. I mean, we all know how to drive. We know what's right and what's wrong. We still have a lot of accidents. Why? How do you control that huge volume of traffic that's moving around the world? And the same applies to mine.
In your experience, the accidents come more from design or
no?
I wouldn't think of design actually. I would say it's sometimes we get confident with operations and somehow there is not full security measures to
I have
to deal with some of them.
I've worked now in many mines around the world, and in general, I find the level of effort, both in civil engineering and in mining, to understand the problem, to find the right designs, is improving, and I would say in general is good. I would say most of our accidents today are accidents, literally accidents, that you have designed pillars in this way for this kind of rock mass, in this kind of stress field, and there's a fault you didn't know about.
I see.
And that fault fails, and your design doesn't apply to faulted material because you never had that fault in the analysis. That's really nobody's fault. That's part of our learning experience. And in some cases, we may get to the point where we can't learn enough to stop all accidents.
Exactly. It's very difficult to. It's a tough topic. It's a tough topic. The issue of accidents.
Yeah.
There are many stakeholders in the game at that level. So
well, if you look at this slide, go back for a moment, and look at the slide on the screen of the risk analysis. Yeah, the one on the screen here of risk analysis.
The first one or which one?
Anyone.
Oh, okay.
Anyone. You'll see that what we've got here is this dotted line and the red and the pink block underneath it. This zone. Can you see what I'm pointing out? This zone is called the Alarp region, as low as reasonably practicable. And obviously, there are a lot of situations that are outside that zone, but commercial aviation, home accidents, some of these fall underneath that dotted line. And they are those over which we have the best control. They're still accidents. I mean, there are still aircraft that crash. That's a very good place to be. 1 in a million chance of failure, but 1 in a million can still happen. And the same applies to underground engineering. So we try very hard to get as low as possible in number of fatalities, and particularly in open pit mining, because we are destroying the rock.
Actually, literally
destroying
to the size of a sand.
Yeah. So that means we have to be very careful with our control of safety, with our designs, to try and keep this little purple ellipse under control. And I think we're doing pretty well. Will we ever reach zero? Probably not. Not in my life, anyway.
Yeah, it's a very interesting chart.
It is
very telling.
Yeah,
very telling. Very telling. We have some more questions. We have actually a lot of questions. Now we have a lot of questions. Jorge Sandoval, he says, Dr. Hoek, what are the most important scopes and limitations for the use of the Hoek and Brown criteria in geomechanical mapping for a pre-analysis in a tunnel stability?
That's a complex question. First of all, we have to say that there are 2 ranges, the extreme ranges of tunnel behavior. For very strong rock, the range is the problem is brittle failure, as I've described in South Africa, for example, Australia, in all over the place. If you have a very strong rock, a granite or a granodiorite or a porphyry, very, very strong, intact, solid rock, but you have very high stresses because you're working at great depth. And now many mines are approaching 4 kilometers of depth. That's very, very high loading. The danger there is rock bursting. So literally, when the rock fails, and it doesn't fail very often, but when it fails explosively. And the damage will be huge. That's the one end. The other end is what I would call the soft rock end, where you are dealing with a mixture of materials, which could be some good rock, but some very poor quality clays, materials that are weathered, sandstone and clay shales and things like that, that have very poor long-term characteristics. The problem is that if a failure occurs, it can propagate slowly if the geometry doesn't change. I mean, the geometry could change. For example, if you're talking about slope stability, if there is a failure of the toe, that changes the whole geometry of the slope. And so you can have sudden failures resulting. But in general, the soft rock end, the criterion is gradual movement, gradual deterioration of the rock mass, and failures which are rather slow in developing, but can be quite catastrophic in their end results. So those are the two extremes that I think, if I understood the question correctly, are these the extremes that I see as being critical. The Hoek-Brown criterion can be applied in both, but it's like numerical analysis. You can put a number in. Do you understand the number enough? Do you really know what the magnitude of that number is? In some cases, yes, as in Chucky. In some cases, absolutely no. You just have to guess. And particularly if you're doing a design of a brand new mine about which you know very little, and you say, as I described earlier on an analysis I saw done, where they mined the whole pit in numerical modeling. So they had a numerical modeling of each bench level. The failures were predicted in the rock, assuming the rock properties that they thought they knew. And it was a very good analysis. Did they know enough? I'm not sure, but it gave the designers of the mine a very clear understanding of what could happen. And you could see if you changed the shape of the pit in one area, you had many more failures. And now you might say, okay, when you actually get to mining that, maybe it fails, maybe it doesn't. But at least the designers had some idea of what could happen. And that's better than nothing. Way better than nothing.
Thank you very much. Thank you very much for that answer to the question of Jorge Sandoval. There is another question. How many questions can we make? Because we have a lot.
Well, it's up to you. For me, it doesn't matter, but you obviously have a time scale.
Okay. Let's see if we can have maybe 5 more questions or something like that.
Sure.
There is a question from GHC that we are gonna do at the end because it's in the plan of the talk, okay? Para los colegas de GHC consultores que están ahí, enviaron una pregunta desde Panamá. Freddy Valeriano, he asks, Dr. Hoek, what are the issues that you consider require more research and should be addressed in the future related to rock mechanics applied to mining? Today is the International Day of mining. So it's a very proper question for the day. Well,
I would say we have come a huge distance since the last 50 years. The technologies that are available today, and I'm not talking about the Hoek-Brown criterion, I'm talking in general terms. the technologies that we have for mapping the rock mass, the understanding that we gain from that mapping of the rock mass properties, the behavior of faults and so on, the understanding of the role of geological features in terms of the topography of the site, the existing faults, how that particular piece of the Earth's crust was developed. We have good understanding of many of those things, and I'm not only talking about mining, because much of my work has been in civil engineering in countries like Greece, where there are very complicated geological formations that have to be dealt with. So we have a good understanding of all of these, and we have developed techniques that can be applied to most of them. And I can't think of any major gaps in that collection of tools, analysis techniques, understanding of the design implications, the risk analysis issues. But we are faced with a huge amount of problems when you go onto a new site, say, and you say, I'm going to design a new underground mine or a new open pit here. You have a huge problem of how do I mobilize enough resources to collect that information. And I don't know if you noticed on some of the slides in Chuquicamata, the database has been built up of something like 120 kilometers of drilling and 120 kilometers of bench mapping. That has taken 20 years to do. Obviously, if you're starting a new mine, you don't have 20 years. You have next year, I'm going to start mining. So you have to take some big jumps in your assumptions. That's the biggest problem. I think we have all the tools that we really need, and it's not difficult to develop new ones if we need them. We know that you get a few people together, they can develop a new tool. It's how do we apply this to a subject where we're dealing with extremely large volumes of rock masses. How do we mobilize the right effort to get the information we need? That's a big challenge.
In that regard, what do you think of the potential capabilities that tools like artificial intelligence will have in the future regarding rock mechanics, based on all the available tools that we have in different areas, like mapping, numerical analysis for stability, rock classification? You can see even sometimes in different conferences or technical discussions about softwares that allow to identify the type of rock. What is your opinion about those tools? Are they here to replace the geologist or the geological engineer, or they should be carefully considered?
I think
what has your experience been on that?
I think it's a great area of potential, because if you think about it, I've described some of the things that I've done over a period of 60 years, one man over 60 years. How many rock mechanics engineers are there with my kind of experience who can do that development? And a lot of it has been very well formulated numerically, so that the idea of artificial intelligence being applied not only to the numerical analysis, but to the thinking processes that evolve are very attractive to me, because you could visualize the kind of thing I described that Stefan Roberts and Kirsten did on a new mine in Chile, and it was up in the general Chuquicamata area. I don't think it's been developed yet, where they effectively mined the mine theoretically. But it required a huge amount of personnel time. Why can't we use artificial intelligence to help us in that field? So there I see a great potential for simply defining the problems that could occur and turning the computer loose and saying, okay, explore for me what happens, what could happen. Because we don't have enough people to do that work.
Exactly. And the resources are are immense today. I mean, there is even a technology I have heard recently about that it's called digital twins, in which you pretty much replicate an entire mine, the operation, the properties, and all it's like a full replica of a mine inside a computer that is able to forecast and predict different scenarios depending on how the variables are changed. It's mind-blowing.
That's exactly the kind of analysis I described maybe 20 years ago that was done by Stefan Robertson Kirsten for the mine in Chile, where they did all of those things.
Oh, I see.
So they built a mine and they mined it, and they said, these are the things that can happen. But the resources required to do that were enormous. There were not enough people.
Now it's way easier.
They did a very good job. The problem is, who defines what are the problems and what method of analysis are going to be used?
Exactly.
We're going to be in rather murky ground. It's like somebody learning to drive. It's obvious what you've got to do, but you have to learn all the tricks. And that's going to take a little bit of time.
I agree. Yeah, that's very, very true. Okay, so we have other questions here, Professor. Catherine Toro, she asks, there are rock masses of very poor quality due to the high fracture state they present, and poor conditions due to discontinuity or... Oh, this is the question. Sorry, I misread it. So it says, are there rock masses of very poor quality because of the high fracture and joint state and poor conditions of discontinuities, or it's because of their low resistance? That's the question from Catherine.
There isn't a simple answer to that because you get both. I've seen many.
I would say so.
I've seen many rock masses which are just broken to pieces. And the photographs you saw of the Chuquicamata wall are like that. I mean, okay, the blocks are still maybe 3-5 meters size, but over that scale, it looks like soil. And the faults are very, very dangerous.
Right. Yeah.
So all of those occur. And now the scale, if you're talking about underground mining in Chuquicamata, you're talking about a tunnel, maybe 5 meter span. So it's feasible. You could only have one fault in otherwise intact rock. So the problems are different, and the methods you tackle them are different. But nevertheless, the problems are potentially there in every situation. And if you look at the Chuquicamata mine, if you look at the west fault running through it, that's a pretty big fault. And the material uphill on that is very heavily broken and very unstable. The granodiorite on the other side of the fault, below the fault and across the other side of the pit, is very high quality. It's still broken, but it's very frictional, it's very strong. So you could have slopes, as I say, of 53 degrees at the bottom of the pit in that kind of rock. On the other side, you're talking about slopes maybe of 30 degrees before they are stable. So huge differences.
There is one question also from Victor Rivero. I think this is a question based on one of your last papers, maybe from 2018, in which you talk about a new approach or new, let's say, considerations about the Hoek and Brown criterion. He says, after many years of applying the Hoek and Brown envelope in mining, what is the current view, your current view, on the use and possible overuse of factor D in back analysis process?
The factor D is an unfortunate addition to the criterion and it came very late in the development because we realized that we had not allowed for blasting of any kind. And I would say rather poorly defined. It's the best we could do because we didn't have enough information. But it's also very badly used because many people see the factor of D in the equation and they apply it to the whole rock mass, everything. That's a disaster. And that's completely wrong. And I have, in most of my current publications, included notes saying, please do not do that. Apply it only to maybe 1 tunnel diameter around a tunnel, or 1/3 of the slope height in terms of the slope.
For the plastic zone.
Yeah, for the plastic zone or for the damage zone. Otherwise, it gets completely, it distorts the picture beyond recognition. It becomes a useless analysis. So it has to be very, very carefully controlled. Do we know enough about blast damage? Absolutely not. It's the best we could do at the time. I'm now 89 years old and I'm retiring. I'm quitting this business. So I can't contribute much more. Hopefully some other people will look at this question of blast damage and try to refine it and improve it in some kind of ways. But it's not a good parameter. It doesn't match the other parameters in terms of its sensitivity and how much we know about its actual value. But do not never apply it to the whole rock mass.
Thank you very much. Thank you very much for those details. Those are very important details to know. It's always important to know the small letters that
Sure.
every technique has, right? It's and not everyone reads it.
That's right.
And that's a key aspect to consider. We have one question from Catherine Toro again. She has a question, and Catherine says, when you enter the GSI chart, you can find ranges between 20 and 30. Which is the best way to characterize these rock masses of very poor quality? Like I had a similar question actually. Now that I'm in the way I'm progressing with the question of Catherine, and I see the point. How do we deal with that? As a soil, as a rock, what are the key considerations to take? That rings a bell with many of the problems that I have seen in practice.
Can we go back to the other presentation, the Hoek-Brown presentation?
To the
lecture.
To the lecture, to the video. You want to go to the
video? Yeah, to the video.
To the video. I wonder if Karina here can help me. Karina, maybe you can help me.
Yes, give me a minute.
In what minute, Professor Hoek?
We want to take this one off and replace it with the video.
Okay.
I want to refer to some slides in the video.
Okay, I will stop sharing my screen and I will let Karina take it from there.
So this one we can take off. That's it. Okay. Now let's just go back. If I can I control this in any way? I want to come near the end of the presentation, about there, yeah, and a little bit further. Actually, wait a bit. Maybe back a bit. Maybe about here, and back a bit more.
Maybe a bit more. A bit more.
Bit more here.
I think Professor is looking for the charts in which there were pictures of rocks and engineers in the picture.
Yeah. Bit more. Bit more.
I think we are close.
Yeah. Bit more. One more, I think. This one. Okay, here's a good example. So you have on the top left, you have GSI is 80 to 90. And this is very hard rock. This is granite in Canada to depth of about 1,000 meters in a uranium mine. And you can see that the failure is spalling. The rock is intact. And the high stresses cause spalling, which is little thin flakes that fail in tension that fall off. So that's at the one end. And at the other end, if you like, 10 to 20 here is in Greece, and that's in very heavily deformed sedimentary rocks. And you can see the pieces are broken up. So that is very close to a soil. I would not call it a clay. It could become clay depending on moisture content and the mineral composition. So you could have zones of clay, but generally it's just very, very heavily broken rock. And then this one here is a good one, 30, and you can see this is in Taiwan, and it's a rock mass that's obviously been distorted by the formation process of the continent, of the island of Taiwan. So there are many pieces of broken rock in there. There's some bands of very strong, I don't know what they are, maybe granites. And that's a mixture. These kind of rocks, you could say, we can treat as a kind of soil, and it has properties in many cases. These on the low end here would behave very much like a soil. So you'd be talking about slopes of maybe 30 degrees for stability. You'd be talking about tunnels that basically creep with time. They close slowly with time as the rock deforms. Very difficult to control, and you have to put in very strong, rigid support in order to keep the profiles functioning. This is one here in the middle, and this is a mine in Papua New Guinea, where I'm talking about GSI 45, and that's a granodiorite that has been very, very heavily broken by active volcanic activity. This is an island that has active volcanoes on the island where there are earthquakes every day, more or less, and some big ones, one a year. And so the rock mass, which is very, very strong granodiorite, extremely strong, has been broken into what you see there, little pieces of rock, maybe 10 centimeters, 50 centimeters, and smaller. And compare it with this one. This is granitic rock in Canada, which obviously has been deformed by the deformation of the crust of the plate in that region. And so you have a nice orthogonal pattern of failures, but the rock is very strong. The shear zones are very rough. And so that actually is a very strong rock mass. This is weaker because there's more mobility in it. These are much weaker because of the soft elements and the complete lack of structure. And this is very close to a soil. So there's a picture of the whole transgression. I don't know if that helps you, but that's what you look for when you're looking for the first time. Where am I in this kind of job?
I think that's very important, actually, because I can tell only on some cases I have seen in the US and South America, particularly Ecuador, Chile, in which you can see a slope, and from what you see, you can see a rock.
Yeah.
But after the landslide happened, you see rock powder, basically. You don't know if it's a gravel or a soil or a rock, but you can see a very healthy material just from looking in the eye. And that's when it comes the expertise of an engineering geologist or a geologist.
Absolutely.
So,
rock mechanics without good geology doesn't
absolutely.
work.
Exactly.
Not
exactly.
work. Yeah.
Absolutely.
And
absolutely.
Paul Marinos, who unfortunately has died, was one of the best engineering geologists I ever worked with, because he had a very strong engineering understanding, but he was a superb geologist. And he could look at the topography and the cuts in the road and so on, and make astounding predictions.
Very nice, very nice. You had a long collaboration with Professor Marinos.
Yeah.
Professor, we are with the last question. With the last question.
Is that because of time?
No. We made it. We made it. Somehow we made it to the last question.
Okay.
It's from Christian Vitola. And it says, how would you focus all these considerations of rock mechanics in your mining experience applied to tunnel engineering for roads?
I have worked in every field of rock engineering, and tunnel engineering for roads is no exception. All of the consideration we've talked about here
apply.
But you're dealing with a much tighter configuration. A slope could be 1,000 meters high, a tunnel maybe 10 meters, maybe a bit more, but it's a restricted range of rock. What you have to be very careful with in tunneling is that you don't apply the same gross assumptions that we're making here, for example, for slopes. You're looking for the overall behavior of that rock mass to give it a C and a phi or an MI and SA parameters. And so you can be rather loose in your judgment. In the case of a tunnel, you're dealing with a much smaller volume of rock, which you have to define in much more detail. Typically, you're looking at the tunnel. Let's say it's a 5-meter diameter. Maybe that's too small. 8-meter diameter tunnel. You're looking at a rock mass which may be 24, 25 meters in diameter. So that, let's say, one diameter of tunnel around each tunnel is the rock mass that really impacts how that rock mass is going to behave. It's very seldom you would put in anchors, for example, longer than the diameter of the tunnel. Occasionally you may have to, but in general, your anchors or your rock bolts are maybe 1/5 or 1/4 of the diameter of the tunnel. So you're limiting it much more in size. The thickness of your concrete lining very seldom exceeds 1 meter, maybe it's less. And typically in designing a tunnel, what I've had to look at many times is a sequence you go through to identify the rock mass, its characteristics, do whatever testing you need to do whatever mapping you need to do to come up with reasonable values of its strength behavior. Realizing that that strength will vary a lot within the tunnel, rock surrounding the tunnel. Then you look at the size of the tunnel. How is it excavated is very critical, because I've worked in some very, very poor rocks where we've designed multiple stages of excavation. So you could start with a small top heading, 2 side drifts, and then benching down and supporting every stage of the tunnel as you go. So the sequence of excavation and of reinforcement of support installation is very important. And you've also got to look at the time-dependent behavior. Once you've got the tunnel constructed, what are the possibilities that in 5 years or 10 years, there may have been deterioration of the rock, and why? There's got to be some geological explanation for the time-dependent behavior. But you might have to say, I have to design the tunnel heavier support to take care of this particular rock, because I know, like this rock here, that it's going to creep in time. The stresses are going to change. The failure patterns are going to change. So all the procedures are exactly the same, but on a different scale with a different emphasis on how do you collect the information, how do you analyze it, how do you take scale into account. the basic technology is the same. Does that answer your question?
I think so. I think it should. Yeah, Christian will let us know, but it absolutely. And well, it seems that we are at the there have been many questions, and there has been a lot of interaction, and it seems to me that you have enjoyed also a lot to discuss about all these fascinating topics.
Sure.
So I'm very happy that you felt comfortable with here presenting your experience and knowledge with us, Professor Hoek. Taking the, do you remember that we talked about this yesterday? Is that one last request?
Yes.
What is your advice for future generations, for the youth, for the young engineers that are entering this fascinating world of engineering geology, and rock mechanics?
Well, first of all, I would say that you have to have a real interest, because it will occupy all of your time. You can't do this half time. If you decide to go into the field, you have to commit yourself to full concentration. If you're a general civil engineer or a mining engineer, and you need to know a little bit, the information you probably get in any university course or from some of the textbooks is probably enough. It at least tells you when you should call somebody to help you, if the worst comes to the worst. But in many cases, the solutions are simple enough. You can apply them. But if you really want to devote yourself to the kind of intense involvement that I've had in projects all over the world, it is a full-time occupation. And what it means is that if you want to go that route, you have to find a university that is going to offer you the kind of coursework that you require for that. There are very few universities around the world today that offer that depth of rock engineering. There are many more that offer soil mechanics, which is interesting, but it's not rock, it's soil. But I can only think of a handful of maybe 10, maybe 20 universities around the world that I would say you could get a course that's detailed enough that it would take you into the depths of subject that you really need. And it's not necessarily a course that emphasizes numerical analysis. There tends to be a very heavy emphasis today on numerical analysis because of the availability of the tools that we have. Those tools are excellent, and I have no problem with them. But don't take it that a numerical analysis is an understanding of rock engineering. It's what goes into the analysis that really matters. And so that means you have to be prepared to spend some time in the field. You have to learn enough about geology to understand how the geological interactions work and how the formation of the process impacts its behavior. And you have to be prepared to look at the mechanics of each type of failure, because it's really, rock mechanics is really a study of failures. What we're trying to do is to avoid failures. In order to do that, we have to know what causes them and how we can prevent them. So what you're trying to do is to learn enough so that you can recognize that in this tunnel, in this kind of rock, these are the things could happen. And so read widely. I have decided that the last part of my life will be devoted to one thing. This is the last. I have one more lecture to give after this at the University of Tucson in Arizona in October. So this is my second last ever.
Second to last.
Second to last. One more to come. But after that, or before that, I have on the internet, you know, a group of documents called Practical Rock Engineering on the Rock Science website. I am intending to edit all of those chapters. Some of them were written in the 1980s when I was at the University of Toronto. They are old. They do not include many of the things we've learned in the last 40 years. I want to try and update them so that I leave behind a set of practical guidelines of what you can do to analyze slopes and tunnels and dams and what have you, and what you can do to understand the rock. That's my last goal, if you like.
A full edited book.
It's necessary because there are not enough practical books that take you through a case history one by one and say, this was a tunnel in this kind of rock, this is what happened, this is how it failed, or if it maybe it didn't fail, why it didn't fail, this is the kind of support that is necessary, and here is a photograph 10 years after construction showing that it's still working properly. That's the kind of papers you need to find and read from people who've done it in the real world.
That is I'm sure the entire full community of engineers, geologists, and mining engineers are looking forward to Professor Hoek. I mean, that definitely will be a massive hit, that book.
Well, it may, I mean, it's not a book, it's just a collection of chapters, as you know. And it's very popular now, but I have to update it. It's really out of date. So be careful when you read that. The present volume, it is 20 years old or 30 years old, and I need to update it a lot. I wish there were people who wrote, instead of pages and pages of mathematics, wrote some real experience of tunnels they'd worked in or slopes they designed or what have you.
I agree. I
To
agree.
me, there's a big deficiency of that kind of literature.
Yeah.
Just case histories.
Yeah. Unfortunately, field experience doesn't come in books. Unfortunately.
Well,
Unfortunately.
yes and no. I mean,
Yeah, of course.
As I think of, all involve significant field experience. Professor Marinos used to take his students out every year, like 300.
Yeah, that's what I mean. I mean, you have to go out. You have to go out and go out and go out, and don't miss the opportunity to go to the field.
That's right.
That's always my advice to the young engineers too. It's very important. Very important.
Don't get carried away by reading the mathematics. Go look at the real rock.
Absolutely.
Okay.
Absolutely. Well, we have addressed so many questions, and we have had such a nice discussion. We have been 2 hours talking about rock mechanics, and we are endlessly thankful for your time, for your dedication, for all that you have done for our career. And thank you very much. Thank you very much. I think it's been a wonderful discussion, and we have learned a lot from you in this nice lecture. Thank you very much. Thank you also to Karina. I mean, Karina, without Karina, we cannot do anything.
You need that help.
So thank you very much, Karina. Thank you very much, Dr. Hoek. Thank you, everyone, for coming to this great lecture. And we are going to see each other very soon again in the seminars of geotechnical engineering of the University of Chile. We are going to stay here with Professor Hoek just 1 more minute, but we say bye. We say bye until the next one, and we cut the transmission here. So thank you very much. Thank you very much. And thank you, Karina. Thank you, Professor Hoek.